Good day, everyone. In the last lecture, we characterized how good an estimator is and raised a few questions that we will be addressing here today, namely how we can design a good estimator and also how well we can do in a given estimation problem. Since our goal is to design a good estimator, the first approach that one can naturally think of is to start by choosing a performance metric that quantifies how good an estimator is, right? For example, those metrics that we saw last time, but other metrics are also possible. And then we try to find the estimator that is optimal in terms of that metric. So this can be thought of as an optimization problem where we try to minimize the performance metric. Here we are assuming that less is better, right? That's why we are minimizing and not maximizing. And the optimization variable is our estimator, right? Therefore, a function, and it runs across all possible estimators. However, this approach is not as simple as one may think of at first glance because the metrics that we typically use depend on the value of the parameter that we want to estimate, right? This can be seen by noting that the metrics that we discussed last time involve an expectation across all realizations of the data, and therefore the distribution of the data shows up there. The problem is that what estimator or which estimator is best depends on the value of theta. Therefore, for instance, for this value of theta, we see that this estimator here is better than this one. However, for other values of theta, we see that the opposite is true, right? And if we knew what is the value, the true value of theta, then we could try to solve this problem for that specific value, right? However, the value of theta is unknown. That's why we are estimating it, and therefore we don't know on which value of theta we need to focus on here. However, one may think that such a difficulty wouldn't arise if there was an estimator that is better than any other estimator for all possible values of the parameter. So let us adopt MSE as our performance metric. The reason is that the bias and the variance standalone are not suitable metrics for this purpose, as it will become clear later. And let us define the uniformly minimum MSE estimator as an estimator theta hat whose MSE is less than or equal to the MSE of any other estimator theta hat prime for all values of the parameter. However, it can be easily seen that such an estimator does not exist in general, except for the generate cases where one can obtain the true parameter exactly from the observations. For example, in the cases we discussed last time when there is no noise. And the proof follows from a very simple argument. Remember that last time one of the example estimators that we discussed returned the same value for all realizations of the data. So let's consider estimators of that kind by defining theta hat sub alpha as an estimator that always returns the estimate alpha no matter what data vector it is given. And remember that such an estimator satisfies that the MSE is 0 for when the true parameter equals precisely that alpha. We also plotted the MSE. It was a parabola that touches 0 when theta is precisely the value of that it returns. So we can see that for any possible value of theta, we can define such one estimator of this kind. And therefore, if an uniformly minimum MSE estimator existed, then it would need to have MSE equals 0 for all possible values of theta. And that would imply that theta can be obtained exactly, because otherwise it's not possible to attain 0 MSE. So we have created and killed one estimator in a single slide. This leaves us in a pretty dramatic situation. All our attempts to come up with a satisfactory estimator have failed. So let us analyze what was the problem so that we can find a way out. To this end, let us note that our goal was to outperform all possible estimators, and in particular we failed to outperform these estimators theta sub alpha hat, which, if we think of it, they are horrible estimators. They just disregard the data, return always the same value, and therefore they are extremely biased, and their MSE is extremely large unless we are very close to the value that they return. This suggests that we were trying to compare with a family that it is too large, and therefore a sensible approach would be to lower our hopes and focus on a subfamily of estimators, for instance, in the family of all unbiased estimators, right? So let us now pursue this more modest goal of trying to find the unbiased estimator that has the lowest MSE for all possible values of theta. And if we remember the expression that we deduced in the previous lecture, the MSE equals the variance plus the bias square. And since the bias is 0 for all these estimators, then the MSE and the variance are the same, and we can replace the MSE here with the variance, right? So the solution to this problem is the so-called the minimum variance unbiased estimator, or Mvu estimator, and it is therefore unbiased, and its variance is less than or equal to the variance of any other unbiased estimator for all possible values of theta. This reasoning is actually very instructive because it captures very well a common procedure in statistics. So actually being the best is a matter of who you compare with. Some people joke that statisticians first think whether they are the best statisticians in the world, if not whether they are the best statisticians in their country, if not in their city, and so on. What is clear is that I am the best piano player among all piano players in this room right now. So setting stupid jokes apart, the good news now is that the MVU exists in many cases as opposed to the uniformly minimum MSC estimator that we invented. However, it is still possible sometimes that there's no estimator, no unbiased estimator whose variance is smaller than the variance of any other estimator for all values of theta. There are several approaches to try to find an MVU estimator. And one of them is by following the theory of sufficient statistics, specifically the so-called Rao, Blackwell, Lehman, Scheffe theorem, which we will not be covering in this course, but you can find an explanation in, for instance, in the book by Stephen Kay. Another approach is to use the theory of best linear unbiased estimators, or also called BLUE, where the family of candidate estimators is further reduced to those that are not only unbiased but also linear. And this sometimes also provides an MVU estimator. The approach that we will be adopting here is based on the so-called Kramer-Rao lower bound, which is a fundamental limit that provides a lower bound for the variance that any unbiased estimator can attain. And as a fundamental limit, it provides a way of quantifying how difficult a problem is. So, for example, one can use it to establish that in a given problem there's no ideal estimator, that is no estimator with zero bias and variance. And since it is a lower bound, it can be used as a benchmark for unbiased estimators, yet in many papers it is also used as a benchmark for biased estimators. In that case, it is not a lower bound, and a biased estimator can obtain a lower variance than the one specified by this bound. So it is not actually a bound, but it is a reference. So as I said, this will sometimes provide the MVU, and it relies on the so-called likelihood function, which we are going to discuss next. The likelihood function is a very famous function, especially in statistics and machine learning, and even more now with the advent of deep learning. However, it seems that many use this function without really knowing what they are doing. So to understand what this is all about, let us assume that our data adheres to a continuous distribution, and let us look at the PDF from two alternative perspectives. So on one hand, the PDF sort of quantifies how probable an observed value is for a given value of the parameters, right? Note that I am writing probable between quotation marks, because the probability that a continuous random variable takes exactly a given value equals 0, right? This is precisely the definition of a continuous random variable that we discussed in our review video on probability theory earlier in this series. So to bypass this technical subtlety, let's look at the probability that the data takes a value close to a given alpha, where close to in this case means that the data takes a value in this interval defined by a small positive constant delta, right? So as we know from probability theory, this probability is given by the integral of the PDF on this interval, right? And if delta is sufficiently small, then this integral can be approximated by the width of the interval times the value of the function we are integrated on the at the center of the interval, right? So this is a property of Riemann integrals. The bottom line is that the probability that x0 takes a value close to alpha is proportional to the PDF evaluated at alpha. And an alternative perspective to the PDF is that it quantifies how likely a parameter value is for a given observed value. So suppose that we observed that x0 took the value alpha, and we wonder whether it was obtained from a distribution with parameter theta1 or a distribution with parameter theta2. So following the logic here, we find that this is the probability of what we have just seen when the parameter is theta1, and similarly for theta2. And by looking at the figure, we observe that the PDF under theta1 is less than the PDF under theta2, and therefore this probability is greater than this. Or alternatively, we can conclude that it is more likely that this value was obtained using this distribution with parameter theta2 than using the distribution with parameter theta1, right? So note that we use the word likely, not the word probable, right? We cannot say how probable a parameter value is, because the parameter is a deterministic creature, right? It's not a random variable, and therefore there's no probability associated with it. And using the wrong word here is a very common mistake. The likelihood function is defined to precisely capture this perspective of the PDF. Specifically, for each possible value of the observations, we define a likelihood function that assigns to each possible value of the parameters the result of evaluating the PDF at the data when the parameters are precisely those in the input. So note that this provides the same values as the PDF whenever both of these functions are given the same x and the same theta, and therefore constitutes different views to the same thing. However, from a mathematical point of view, these are creatures that live in totally different worlds. So specifically, we have one likelihood function for each possible realization, and this function goes from the parameter space into the non-negative reals. On the other hand, we have one PDF function for each possible value of the parameters, and this function goes from the data space into the non-negative reals. And the way of reading a likelihood function or interpreting it is as Lx theta of theta 0 quantifies how much evidence the data x provides to support that the true value of the parameters is precisely the one that we are indicating here. This is the interpretation that we have to keep in mind whenever we deal with likelihood functions. When we plot it, the likelihood function generally looks very different from the corresponding PDF. An exception is, however, the likelihood function for the mean of Gaussian random vector, as in the example of estimation of the sea level, where the parameter capital A plays the value of mu here. So the likelihood function has, of course, the same functional form as the PDF, right? However, now it is a function of mu, so let us express it in a more convenient form so we can see how it looks like. To this end, let us start by expanding this square and applying the property that the exponential of the sum equals the product of the exponentials, to take all the terms that don't depend on mu out of this exponential. And this will be expressed for simplicity using this symbol, which means that the left-hand side is proportional to the right-hand side, and the proportionality constant, this one in this case, is positive. Now let us complete the square. So we obtain this equality over here, and this term, which does not depend on mu, is also absorbed into the proportionality constant. Therefore, we found that the likelihood function has the functional form of PDF with this mean and this variance. So the likelihood function in this case is a Gaussian bell centered at the sample mean. It is remarkable to say that the likelihood function does not necessarily integrate to 1, right? This can be easily seen by noting that the proportionality constant that we put here does not normalize this exponential to integrate to 1. And also for later usage, it is important to note here that the shape depends on the data only through its sample mean. This means that the likelihood function, or the shape of the likelihood function for two possible realizations with the same sample mean is the same. However, this is up to a scaling factor because of this proportionality constant here. And also, it is important to note that the width of the bell increases with the noise power and decreases with the number of measurements. This means that for smaller noise power and more data, this becomes more peaky. And this is an effect that we will soon investigate. The likelihood function, when the data follows a discrete distribution, is not obtained from the PDF, obviously, but from the PMF. This is illustrated in this example where the data are Bernoulli distributed with parameter beta, and the samples are independent along n. Recall that this is the PMF of Bernoulli random variable. Again, the likelihood function shares the form of the PMF, which, due to independence, equals the product of the marginal PMFs, and therefore it can be expressed in this way. Now, by applying the property that the product of the exponentials equals the exponential of the summation, we obtain this expression, and now we just need to recognize that the sum of samples equals n times their average. The likelihood function, therefore, is the product of these two terms, and it is instructive to look at each term separately. If we plot the first one, we see that it is a function from 0 to 1. The way it goes from 0 to 1 depends on the exponent. And the same applies for the second term, but it goes from 1 to 0. This figure shows three likelihood functions, each one corresponding to a different realization of the data when the number of samples equals 7. In this first curve, only one out of the 7 samples was equal to 1, the rest were equal to 0. That is why their sample mean equals 1 over n. And similarly with the other curves. The first thing that we observe is that the likelihood function looks totally different from the PMF. The second observation is that the maximum is attained at the value of the sample mean. Note that the true value of the parameter can be anywhere on this axis, right? Because the likelihood function doesn't depend on the true parameter. It depends on the data. However, it is very likely that the true parameter is close to the maximum, and this is a fact that we will be using later in this course. Another important remark is that in practice we don't typically deal with the likelihood function itself, but with the log likelihood function, which is just the result of taking the log. This is motivated by practical reasons, such as to avoid numerical problems, but also due to theoretical arguments that we will not be discussing in this course. The resulting curves, as you can see, are quite different from the likelihood function, but they share certain properties, such as the location of the maxima is exactly the same. So now we understand what the likelihood function is and how it looks. The next step is to use it to quantify how difficult a problem is and how well we can do in a given problem. And to this end, we will be introducing the metric of Fischer information, which is very easy to understand if we look at one example. In this case, these figures show three likelihood functions for the data in the previous slide. Each one corresponds to a different number of samples. We see that the larger the number of samples, the more peaky the likelihood function gets. And as per our interpretation of the likelihood function as a function that quantifies the evidence that the data provides to support a given value of the parameters, we can conclude that whenever we find ourselves in a situation like this, where the likelihood function is very picky, then there is strong evidence supporting a small set of values of the parameter and low evidence supporting the rest of values, right? Therefore, the data in this case is pointing us to very specific values of the parameter, right? There's very little room for doubt. There's low uncertainty, right? We say that the data is quite informative about the parameter in this situation. On the contrary, if we find ourselves in a scenario like this, the evidence supporting a wide set range of values of the parameter is quite similar, and therefore the data is not as focused on specific values, and there's higher uncertainty here, right? The data is less informative. In view of this discussion, it makes sense to measure how informative the data is by looking at how picky the likelihood function is. And the way of quantifying how picky a function is in mathematics is by means of the second order derivatives. So we will be using this expression as our starting point. The minus sign here owes to the fact that the second order derivatives are negative in these regions, and we would like to come up with a positive or non-negative information metric, right? The reason is that having negative information is not something that can be easily interpreted, right? So what would it mean that the data provides negative information about the parameter, right? But still, this quantity depends on the specific realization. And we saw in the previous lecture that relying on a single realization is not very useful. So it makes more sense to actually consider its average across all possible realizations. So remember that whenever we have an expectation and we are not clear about what it actually represents, it is very instructive to express it in integral form. So we see here that this average runs across all possible values of the data vector, and that the PDF here depends on theta. Note that what we are averaging also depends on theta, and therefore what we have defined here as the Fischer information will be a function of theta and can be understood as providing higher values, returning higher values whenever this value of the parameters is easier to estimate. With these ingredients, we are now ready to present one of the most important tools in estimation theory, which is the Kramer-Rao lower bound. So consider a problem of the general form that we have been discussing so far, where the parameter that we want to estimate is a scalar parameter, so only a single number to estimate. And assume that the log likelihood function satisfies this regularity condition, which we can say that it holds in most cases of practical relevance, but still we need to check it anytime we want to apply this result. So the theorem says that if an estimator is unbiased, then its variance cannot be less than the reciprocal of the Fischer information. So observe that this bound holds for each value of theta, right? And also note that it agrees with our interpretation of Fischer information from the previous slide, where we said that the Fischer information is large for those values of the parameter that are easy to estimate, right? So in that case, this bound becomes low, right? And on the other way around, whenever a parameter value is difficult to estimate, then the Fischer information is low and the Kramer lower bound is high, right? Meaning that the variance when we try to estimate it with an unbiased estimator, it will be large. So it agrees with our intuition and interpretation as well. And the theorem has a second part that states that this bound is attained with equality if and only if this condition is satisfied. So namely, the derivative of the log likelihood function can be factored in this way. So whenever this is possible, this theta hat attains this bound with equality, and we call it an efficient estimator, which will play a key role because an efficient estimator is always an Mvu estimator, and this is what we are after in this lecture. Now let's practice a little bit and see how the Kramer-Rao lower bound looks in a few simple examples. Before that, let's introduce some definitions to simplify our notation. The Kronecker delta is a sequence defined in this way that takes the value 1 for when the input is 0 and 0 otherwise, right? So this is the representation as a discrete time sequence. And recall that the Euclidean norm of a vector equals the square root of the summation of the squares of its entries, right? And from this expression, it is immediate to see that the square of the Euclidean norm equals the sum of the squares of the entries of the vector, and this can, of course, be expressed as the transpose of the vector times the vector itself, right? Remember that we are assuming throughout that the vectors are column vectors, right? And just by using the fact that this is a scalar and the trace of a scalar is the scalar itself, and also that the trace of A times B equals the trace of B times A, right, for A and B matrices of appropriate dimensions, then we see that the square Euclidean norm is also equal to the trace of x times x transpose. So this is the model for the sea level estimation that we have considered so far, right? The noise is Gaussian distributed with zero mean and variance sigma square. And now, using the Kronecker delta, we can write the covariance in this very compact form, right? Note that if n is different from n prime, right, we recover here the 0, right? The right-hand side is 0, and this expression would be saying that Wn and Wn prime would be uncorrelated, right? And on the other hand, if n equals n prime, right, the covariance of Wn and Wn prime equals the variance of Wn, right? And in that case, the right-hand side is sigma square, right? Which is precisely what we have indicated here, right? So this is just a compact notation for saying the same things that we have said so far in this model. And the likelihood function can be obtained in pretty much in the same way as we did before. This model presents or provides the value of each sample separately, and that's why we call it the scalar form model. However, it is very convenient to just provide the model in this vector form by indicating that the vector x is a Gaussian, multivariate Gaussian distributed with this mean and this covariance, right? So this is again the same way of expressing this model here. And the PDF can also, or the likelihood function can be expressed in a simpler way than in the scalar form, just by using the Euclidean norm of this of the vector that contains these terms in parentheses here. So with this expression for the likelihood function, we can apply the theorem and obtain the Kramer-Rao lower bound. So the first step, as mentioned earlier, is to apply, to verify that the regularity condition holds, right? This is the first step whenever we want to apply this theorem, although in most cases this condition is satisfied. The regularity condition states that the expectation of the derivative of the log likelihood must be equal to 0, right? So to check if that holds true, we start by looking at the derivative of the log likelihood function, which upon substituting the logarithm of this term here, we obtain this expression. Now one can recognize that the second term doesn't depend on a, and therefore it doesn't contribute to the derivative. So we obtain this expression here. And now we need to apply the chain rule. If you are not totally confident with the chain rule, I suggest that you review the material about derivatives that I left on the same folder as the slides. This equality follows by rearranging terms here, and this one follows by noting that the vector of all ones transpose times another vector equals the summation of the entries of this vector, right? And the summation of the entries of this vector is nothing but n times its average, right? And also we need to recognize that 1 transpose 1 is equal to n, right? Because this vector contains n entries, okay? So we obtain this expression, and we just take this n out of the parentheses, and we obtain this one over here. The next step is therefore to take the expectation of this then we just need to recognize that n, sigma square, and a are deterministic, and therefore this expectation reduces to this expression here. And now, by noting that the expectation of the sample mean equals a, right, we finally established that this expectation is 0, and therefore the regularity condition applies. Therefore, we can apply the theorem that we saw earlier and obtain the Kramer-Rao lower bound. Okay, so let's go for it. The first step is to obtain the Fischer information, and to this end we need the second order derivatives of the likelihood function. We just need to recognize that the second order derivative is the derivative of the derivative, and that we computed this derivative in the previous slide, right? Just by noting this, the value of this second order derivative readily follows. And the Fischer information is therefore minus the expectation of this second order derivative, right? And then it just follows that the Fischer information equals n divided by sigma square, which is very intuitive because it increases with n, right? The more samples we have, the more information we get, right? And it decreases for increasing noise variance, right? So the more variance, the less information. The theorem that we saw before states that the variance of any unbiased estimator cannot be less than the reciprocal of the Fischer information, which in this case it becomes sigma square divided by n, right? So again, it increases with sigma square and decreases with n, right? The problem becomes more difficult when the noise power is large or when the number of samples is small, right? And the second part of the theorem states that this bound is attained with equality if a certain condition is satisfied, right? And this condition can be seen that holds in this specific example, right? So we conclude that this estimator that we have here, the sample mean, is an efficient estimator, right? And it is, of course, also Mvu, right? Because since it attains the lower bound with equality and no other unbiased estimator has lower variance than this bound, right? It means that there's no other unbiased estimator with lower variance than this one here. And this holds in general, right? Not only for this example. An efficient estimator is always an Mvu estimator. However, the converse doesn't hold. So it may happen that there exists an Mvu for a problem, but the Mvu is not efficient, right? So that's because the Kramer-Rao lower bound may be too low, right? Too optimistic, okay? And it is, of course, possible that the efficient estimator may not exist, right? So this will happen when this derivative here cannot be factored in the way dictated by the second part of the Kramer-Rao lower bound theorem that we saw earlier. Okay, so let's now look into a slightly more general model in this case, we now assume that the term here, the signal term, is no longer a constant as before, but now it is allowed to depend on the parameter that we want to estimate in other forms, right? So for instance, this signal can be just a cosine whose frequency is theta, okay? And this can be expressed similarly in vector form, right, as before, to get more convenient expressions, right, just by defining this vector as sub theta, right, just stacking all the values of this signal, okay? And even more compactly, we can just say that the vector x has this mean and this covariance matrix. The problem is given x to estimate this theta, right? So this applies, for instance, to frequency estimation, not only for DC level estimation, right? So it's more general. The Kramer-Rao lower bound in this case can be expressed in this way, right? It will be sigma square divided by the Euclidean norm square of the gradient of the signal vector, right? This is of course by what we said about Euclidean norms and by the definition of a gradient. This equals just the sum of the squares of the derivatives of the entries of this vector here, right? So if you have any trouble in to remember what is a gradient vector or a gradient matrix, I encourage you again to visit these notes on derivative that I mentioned earlier. As an exercise, you may try to prove this expression, right? It's similar to what we have done before. And as a sanity check, you may see whether the bound that we obtained in the previous slide is recovered for this special case, right? So when this signal is just a constant, right? All entries of this vector equal a, right? Or theta in this notation, okay? But all that we have said so far about the Kramer-Rao lower bound holds only when we want to estimate a single scalar parameter. However, in practice, we typically want to estimate multiple parameters at the same time, right? So for example, we may be interested in estimating both the mean and the variance of a random variable, or even the entire covariance matrix of a random vector, right? So let's generalize a little bit our model. Here, this theta is now a vector with m entries, right? So we have m scalar parameters to estimate here. And the problem is, again, given the data, to estimate this parameter vector. The performance metrics need also to be generalized, right? So for example, the MSE can be generalized in this way as the expectation of the Euclidean norm square of the difference between the estimate and the true parameter vector, right? And an example could be this one, where x has this distribution, and we are interested in estimating both a and sigma square, right? In this case, therefore, this capital M equals 2, and our vector of parameters contains 2 entries. We already discussed this a couple of lectures ago. But this formulation is still not general enough to accommodate many practical problems. In some cases, we are not interested in the parameters themselves, but in functions of the parameters, right? So, for example, one may be interested in estimating the body mass index of a person, which is a function of the weight and the height of that person, right? So let us consider this same model where we have multiple scalar parameters. And in this case, given the data, we want to estimate a function g of the parameter vector, right? Where g is a function that returns a vector in RQ, right? So we have possibly q functions of the parameters, right? That's why I'm writing an underscore under this the symbol for the function. We also need to extend the performance metric, right? So in this case, the MSE can be generalized in this way. The squared Euclidean norm of the difference between the estimate of this the function of the parameter minus the function applied on the true value of the parameters. Okay. So this is one possible example. In this model for DC level estimation, we may be interested in estimating the so-called signal to noise ratio, which is just the power of the signal term, right? The square of this amplitude divided by the power of the noise, which is precisely the variance of the noise, right? This problem occurs especially in wireless communications, or in general in communications, also in speech, image processing, and so on. What remains in this lecture is therefore to provide the Kramer-Rao lower bound for these two more general scenarios. So let's start by looking at the estimation of vector parameters. So let's start by looking at the case where we want to estimate a vector parameter. This, as we said, can happen when we have multiple parameters to estimate, right? So, for example, we want to estimate the blood pressure, sugar level, and cholesterol level of a person, right? So in that case, there would be three parameters to estimate. So we adopt the formulation from the previous slide, and in this case, our estimator will be, of course, a function of the data that returns some vector in the parameter space, which in this case is contained in Rm, right? So our vector estimator is actually a vector of m entries, right? So each of the entries of this estimator can be thought of as as a scalar estimator for one of the scalar parameters, right? So this could be the estimator for the blood pressure, and this one could be the estimator for the cholesterol level, right? But we do everything at the same time because all the parameters are unknown. And before presenting the main result, we need to generalize a few metrics to this general, more general case, the case of vector parameters. So in the case of the bias, the generalization, it is straightforward, right? So now this second term is a vector, right? and this first term is also a vector, right? Because it's the expectation of the estimator, and our estimator is a random vector. Okay, so it's the expectation is a vector of the same length. The covariance is follows just the definition of a covariance of a random vector, right? So the vector minus its mean times the vector minus its mean transpose, and we take the expectation across realizations, right? And it is also useful to define the variance, right? So variance is typically associated with random variables, but it is also useful to talk about the variance of a random vector and to define it in this way, right? As the expectation of this square Euclidean norm, okay? And just by using the fact that the trace and the expectation permute and the properties of the trace and Euclidean norm that we discussed earlier, it can be shown that the variance is nothing but the trace of the covariance, right? So note that the covariance contains in its diagonal entries the variances of the corresponding of each entry of this vector, right? And just to ensure that we are all on the same page, let us review some linear algebra concepts. We will be using this notation to denote that the matrix A is a positive semi-definite, which remember we say that the matrix is positive semi-definite when this product is non-negative for all vectors x, right? And for positive semi-definite matrix, it can be easily seen that its diagonal entries are always non-negative, right? This can be seen by setting this vector x to be the ith vector of the canonical basis, right? The one that has a 1 in the ith entry and zeros elsewhere. And it is also possible to show that that a matrix is positive semi-definite if and only if the eigenvalues are non-negative. Actually, many people use this condition to when they want to define a positive semi-definite matrix because this is equivalent to this, right? And this notation, A greater than or equal to B, will mean that A minus B is positive semi-definite, okay? So, but we express it in this way for convenience. So now we are ready to present the main result. The regularity condition that we need to assume is a straightforward generalization of the condition that we saw for the scalar case. Here, as we have, however, a gradient, right? In the scalar case, we have a derivative, right? But this is expected because now we have a vector parameter, okay? So the theorem states that if an estimator is unbiased, right? So using this notion of bias here, then its covariance matrix needs to be greater than or equal to this matrix here. This inequality is, of course, understood in this generalized inequality sense, right? So this left-hand side matrix minus this right-hand side matrix is a positive semi-definite. Okay, so what is this matrix? This is just a generalization of the Fischer information to vector parameters. So remember that for Fischer information, we have minus the expectation of the second order derivative of the log likelihood function. Here we have the Hessian, right? It's the generalized version of the second order derivative to vector parameters, to the case where the function depends on multiple variables, right? And this is called the Fischer information matrix, abbreviated as FIM or FIM. So this expression clearly generalizes the expression that we saw for estimation of scalar parameters, right? Because when we have only one parameter, the covariance of this estimator, right, becomes just its variance, right? It would be the variance of this entry here. And the right-hand side is just a scalar as well, right? And it would be 1 divided by the Fischer information. So we see that the scalar case is recovered from this more in general expression. And to interpret this inequality, or this generalized inequality, we can use this second bullet here, right? We said that this matrix minus this matrix has to be positive semi-definite. Therefore, its diagonal entries must be non-negative, right? So this means that the diagonal entries of this minus the diagonal entries of this must be non-negative, right? So we can just write this in this way. This is the ith diagonal entry of the covariance matrix, and this is the ith diagonal entry of the inverse Fischer information matrix. And here we just clarify that the ith entry of the covariance matrix equals the variance of the ith entry of the estimator, right? So this provides the variance separately for the estimation of each parameter. And regarding efficiency, the condition is also straightforward extension of the case for a scalar parameter. Here now, instead of having a derivative, we have a gradient, and now this is no longer the Fischer information, but the Fischer information matrix, right? So whenever this condition holds, then whatever we write here is an efficient estimator. To present the bound for the estimation of functions of the parameters, we adopt the same model with a parameter vector, and the problem, however, is different. Is given the data, we have to estimate a function of the parameters, right? So g is a function that takes a parameter, right? So therefore a vector with m entries, right? This is the number of parameters, right? And returns a vector in RQ, right? Computes a vector of q entries for each value of the parameter vector, right? So an example, as we said before, can be, for instance, if we have two parameters, right? Then perhaps this function returns one function of the parameters and another function of the parameters, right? This is the SNR. But can be, for instance, one parameter is the body weight, the other is the height, and then g returns the the height and the body mass index, right? So arbitrary functions of the parameters, right? That depends on the application that we are interested in. To address this problem, we need to provide an estimator, right? And the estimator should, of course, be a function of the data. Therefore, it takes vectors with n entries, right? and returns a vector in this same space, right? And again, it is necessary to generalize the performance metrics, right? So the bias can also be generalized in a straightforward manner, right? So we just take the expectation of this estimator, right? So again, this is a random vector. I mean, the data is modeled as a random vector, and therefore G hat defines a random vector as well, right? So it has an expectation. This expectation would have also a Q entries, right? And this would be the function applied on the true parameter where we want to evaluate the bias. The covariance is defined as the covariance of any random vector, right? So and this is the expectation of the in this case the estimator minus its expectation times the transpose of this vector, and then so here it is I would like to remark that I am emphasizing here the dependence on x through these parentheses, but of course we can omit this parenthesis x parenthesis whenever it is clear from the context as I did here, right? But it is important to be aware that g hat is a function of the data, whereas g is a function of the parameters, right? This covariance is in turn a function that takes a vector, right? A possible value of the vector of parameters, right? And returns a matrix, right? So this matrix is the covariance of this vector, and therefore it must be Q by Q, okay? And the variance is defined similarly as in previous slide and can be expressed again as the trace of the covariance matrix. So now we are ready to state the theorem. The regularity condition is the same as before. So if the estimator is unbiased, sorry, this should be G of theta, right? Not theta, this is a typo. Then the covariance matrix must be greater than or equal to this expression here. So this is the gradient of this function g, right? Therefore, it must be of dimension m by q, right? It's a gradient matrix, right? It's the transpose of the Jacobian. And the Fischer information matrix is defined in the same way as in the case of estimating vectors of parameters, and therefore the Fischer information matrix is takes a vector in Rm and returns a vector in Rm by n, right? So it is number of parameters by a number of parameters. All right, so this brings us to an end. Let's try to summarize the main take-home messages of this lecture. We started by trying to find estimators whose MSE was the minimum among all possible estimators. And we found that this task is impossible unless in degenerate cases where we can infer the true parameters from the data, right? So, for instance, if in a signal model without noise, right? Then we said we need to reduce the family against which we compare. So we narrowed it down to the set of unbiased estimators. That brings us to the Mvu estimator, right? Which is the estimator that minimizes the variance among all unbiased estimators, right? And we started looking into the Kramer-Rao lower bound because it can provide the Mvu estimator in certain cases. This bound is a lower bound on the variance or covariance of an unbiased estimator, right? So a biased estimator could actually obtain a lower variance, as we saw, for instance, in these trivial estimators that always return the same value, right? And whose variance is obviously 0, right? But any unbiased estimator must have higher variance than the one provided here. The notion of efficient estimator was introduced to refer to those unbiased estimators that attain this bound, right? That their variance satisfies the bound with equality, right? And therefore, it is any efficient estimator is also Mvu, right? So no other unbiased estimator can have a lower variance precisely because of this bound, right? However, the converse doesn't hold, and it is possible that the Mvu estimator is not efficient, right? It doesn't attain the Kramer-Rao lower bound because this one is too optimistic, right? It's too low. It's not possible to attain it. And we also extensively discussed the likelihood function, and we said that it quantifies how much evidence the data provides to support given value of the parameters, right? What is coming up is to address several questions that we still haven't given an answer to. For example, what happens if the Fischer information matrix is not invertible, right? So in the expressions that we presented in the last slides, we needed the inverse of the Fischer information matrix, right? But this is not necessarily, it's not necessarily the case that this matrix is invertible, right? And we also wonder whether an estimation problem can have no solution, right? Or no reasonable solution, right? That's also important to know, so we don't spend or waste our efforts on trying to solve a problem that has no solution. And also, it is important to think of what we are going to do if there's no Mvu estimator for a problem, right? Should we give up, or should we try to find another kind of estimator? So I am not going to answer these questions today. I will leave you with the suspense. So I'll see you in the next lecture.